Neural networks get their power from parameters. More parameters, more capacity to learn. But adding parameters usually means proportionally increasing computation, which hits limits fast.
That's exactly the challenge this 2017 paper confronted. How do we build outrageously large neural networks capable of absorbing vast knowledge without making them impossibly slow or expensive to run?
The core idea they latched onto was conditional computation. Instead of every part of the network activating for every input, only relevant parts activate.
So the network only thinks about what's necessary for a specific piece of data? That sounds incredibly efficient, if it can work.
The authors claimed this approach could lead to dramatically increasing model capacity without a proportional increase in computation. That was the promise, but the practice was hard.
And this paper was about finally making that promise a reality, right? What was the key piece that unlocked it for them?
Their solution was introducing the sparsely gated mixture of experts layer, also known as MoE. This is the fundamental building block we're exploring today.
A mixture of experts. The name itself suggests a team, like different specialists. What exactly does sparsely gated refer to here?
Exactly. Imagine this layer isn't one big brain, but a council of thousands of feed-forward subnetworks, each a potential expert on a specific type of input.
And the sparsely gated part means only a few of those experts actually contribute to the output for any given input, not all of them?
Precisely. The paper states, a trainable gating network determines a sparse combination of these experts to use for each example. This gating network is the crucial switchboard.
So it's not pre-programmed which expert handles what. The network learns to route inputs to the most appropriate specialists.
We actually touched on this concept in case number TCM 033005, conditional computation. MoE shows one of the most effective ways to realize that promise at scale.
It extends our understanding of how conditional computation can be practically applied to build truly massive models.
This foundational paper proved MoE could achieve greater than 1000x improvements in model capacity while remaining computationally efficient. Now, let's build the intuition for how this switchboard and its experts actually operate.
How do these pieces fit together to create a flexible, scalable system?
Imagine a big company. Instead of every employee doing every task, the company has specialized departments. That's the core intuition behind a mixture of experts.
So if a complex problem comes in, it doesn't go to everyone, but to the specific team best equipped to handle it?
Precisely. In a neural network, MoE layers have a certain number of experts, e.g. 8, and each expert is itself a small neural network, often a feed-forward network.
So instead of one large feed-forward layer, it's a collection of smaller ones that can specialize. How does the system decide which expert to use?
That's where the gate network or router comes in. It's the central dispatcher. The blog post says it determines which tokens are sent to which expert.
Okay, so for each piece of input, say a word or token, the router decides which expert or experts should process it.
Exactly. The blog provides an example. The token more is sent to the second expert, and the token parameters is sent to the first network. It's dynamic routing.
That makes sense. It's like sending different types of emails to different departments within that large company analogy.
What if the router is bad at its job? What if it sends almost all the tokens to just one or two popular experts and the others are underutilized?
That's a major pitfall. The text explains, if all our tokens are sent to just a few popular experts, that will make training inefficient. This leads to unbalanced utilization. To prevent this, an auxiliary loss is added to encourage giving all experts equal importance. This loss term pushes the router to distribute tokens more evenly.
So the router isn't just trying to pick the best expert, but also trying to keep the workload distributed across the whole team.
And in the context of transformers, which we covered in #TCM123005, the general strategy is to replace every FFN layer of the transformer model with an MoE layer.
So it's not a whole new architecture, but a modification within an existing transformer design to get the benefits of MoE.
This gives us a solid picture of the components. Now let's zoom in on the gating network itself. How does it technically decide which experts to activate, and how does sparsity actually save computation?
I'm ready to see the actual mechanics of the routing and sparse activation.
The router isn't hard-coded logic. It's a small neural network itself. The blog states, the router is composed of learned parameters and is pre-trained at the same time as the rest of the network.
So the model learns not just how to process information, but also how to best distribute it among its specialists.
The core efficiency gain comes from sparsity, which allows us to only run some parts of the whole system. This is the conditional computation in action.
Does this mean the router predicts which experts are relevant and then literally skips the computation for the others?
Initially, a simple network with a softmax function was a typical gating function. Softmax gives probabilities for all experts.
But if softmax outputs probabilities for all experts, doesn't that mean all experts are still technically considered, even if with a small weight?
That's a crucial distinction. A pure softmax means dense computation. Shazir's work also explored other gating mechanisms, such as noisy top K gating, to achieve true sparsity.
So noisy top K gating is the mechanism that enforces this sparse activation, ensuring only a few experts are truly active?
That's right. The steps are, we add some noise, then we only pick the top K highest scoring experts, and finally, we apply the softmax to just those K experts.
The noise component seems interesting. Is that to prevent the router from always picking the same best experts every time?
The blog explicitly states, why do we add noise? That's for load balancing. It helps prevent a few experts from becoming overly dominant, ensuring a more balanced utilization.
So the noise is a clever trick to encourage exploration and ensure all experts get a fair chance to learn and specialize.
This top K selection is what makes MoEs efficient. By using a low enough K, for example 1 or 2, we can train and run inference much faster than dense models.
The actual computation scales with K active experts, not the total number of experts available.
However, while computation is sparse, a critical point to remember is that all parameters need to be loaded in RAM, so memory requirements are high. That's a key limitation.
So you're not saving memory, just flops during inference. The full model still needs to sit in your VRAM?
We've seen how MoEs work conceptually and mechanically. Now let's look at a powerful real-world example, Mixtral 8x7B, and how these ideas translate into state-of-the-art performance.
I'm curious to see these principles applied to a model I've actually heard about.
Fast forward to 2024, and we have models like Mixtral 8x7B. This paper proudly states, we introduce Mixtral 8x7B, a sparse mixture of experts SMOE language model.
This is a concrete example of how the concepts from the 2017 paper are being used in advanced language models today.
In Mixtral's architecture, each layer is composed of 8 feed-forward blocks, that is, experts. This is that council of specialists we talked about.
So instead of one large FFN, each MoE layer has 8 distinct smaller FFNs ready to be called upon.
Critically, for every token, a router network selects 2 experts to process the current state and combine their outputs. This uses the top K gating with K equal 2.
2 out of 8. That means 75% of the potential computation is skipped for each token, right?
The impact on efficiency is stark. The paper states each token has access to 47B parameters, but only uses 13B active parameters during inference.
That's a huge difference. You get the potential of a 47 billion parameter model with the cost of a 13 billion parameter model during generation.
This is the payoff for all the mechanisms we've discussed. The Hugging Face blog noted MoEs achieve the same quality as its dense counterpart much faster during pre-training.
So it's not just inference efficiency. It's also a powerful tool for more efficient training of massive models from the start.
And the results speak for themselves. Mixtral outperforms or match his Llama 2 70B and GPT 3.5 across all evaluated benchmarks. It achieves state-of-the-art results.
That's incredible. It's essentially a more computationally lean approach delivering performance comparable to or better than significantly larger dense models.
This is where you'd reach for MoE when you want to build models with astronomical capacity, but you need to keep training and inference costs manageable for practical deployment.
So when raw parameter count isn't enough, and you need smart, dynamic allocation of compute, it's about working smarter, not just harder.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.